Okay, so we are starting our unit on forces, and all we are going to talk about today are the most common types of forces, and then how to calculate net force. Okay, this type of math is super simple. You just balance out the sides pretty much. Okay, so this first page that we're going to do is just different types of forces. Let's see what we're dealing with. Okay, so what is a force in the first place? Okay, a force is a push or pull on an object, and it is measured in newtons. Okay, push or pull on an object measured in newtons. Okay, so a generalized force just means that we have a push or a pull on an object. Okay? We are introducing a new unit today, and then that is newtons. Okay, newtons measures force. All right, with forces, we have two main categories, and then we're going to further break those down later in our notes. But the first category are contact forces. And that's exactly what it sounds like. It's going to be a force that directly touches something. Okay? So, me pushing this chair, I am pushing it like I am touching the chair. That's a contact force. Alright? Anything that actually touches the object is a contact force. And then it tells you, so we're going to learn about these examples today. Okay? Those examples are contact forces. The other category are non-contact forces, so forces that act from a distance, okay? Like, if I could move things with my mind, like Matilda, and I moved that chair, I wouldn't be touching it. That would be a non-contact force, okay? Wouldn't today be the best day to, like, if I could actually do that, just, like, freak y'all out, just, like, move a chair? Yeah, that'd be really cool. I'll have to work on that. All right, and then our examples of non-contact forces would be gravitational force, electrical force, and magnetic force. Okay, so if you think about magnets, how they are attracted to each other, it's not like you can see all the little stuff in the air like pulling them together, right? So that is a non-contact force. Okay, what we're going to do now on this first page is we're going to talk about each of those examples by themselves. Okay, are we good on this slide? All right. So we have applied force. This is a very common force. It's done by a person or a machine. Okay, so towing a car, pushing a shopping cart, or sweeping. Okay, so anything that a person does or a machine does. So like an airplane, right? The pilot is applying a force. Okay, that's a person or a machine, applied force. If you see big F with a subscript of a capital A, that is short for applied force. Okay, our second type of force on this page is gravitational force. We are used to this. We know that we're not floating off of the earth because of gravitational force. And its short-term symbol is capital F with a lowercase subscript G. Okay, gravitational force is nothing new to us. Would you say gravitational force is a contact force or a non-contact force? Non-contact force. Okay? Gravitational force would be one of those non-contact forces. Keep writing if you need to. We got time. All right, our next force is called normal force, and it's kind of hard for students to wrap their brain around, but if you don't overthink it, it's pretty simple, okay? So normal force, the force that is pushing back on an object, okay? So our example that it gives us is we have a book resting on a table. The table pushes back with a normal force, okay? So there's not necessarily movement to it all the time, but it's almost always there. Okay, normal force. Its shorthand is capital F, capital N. And then it gives us a few points here. Normal used to mean perpendicular. Many times the normal force is equal to the gravitational force. Okay, so an example of normal force is if I'm sitting in this chair, okay? If normal force didn't equal out gravitational force, I would like fall through the chair. But there is a normal force applied by this chair that's keeping me level and keeping me stable. Okay? Friction forces. Alright, we know what this is. We see this a lot, I feel like hitting the brakes on a car, the tires creating that friction against the road to slow us down. That is a friction force. It typically opposes motion. It depends on the materials involved. Alright? And friction force is capital F, lowercase f. That is its shorthand. We good here? Alright. We also have air resistance. Okay, so like a parachute or anything like that that catches air. That is going to be a type of force just due to air. That one's pretty simple. Special type of friction that is due to air, and we just say capital F, subscript air. Oh shoot, hold on a second. There we go. Alright, with air resistance, we're going to talk about something called terminal velocity. Point where it is not possible to accelerate any longer. This is when air resistance is equal to the gravitational force. Different objects can have different terminal velocities. Okay, so I'm going to let y'all write that down, and then I'm going to explain what that is saying in simpler terms. Terminal velocity. Okay, so I want you to imagine that you are about to step out of a plane and you're parachuting, okay? You step out of that plane and you're free falling, you pull your parachute, and then you feel that big slowdown. Can y'all picture that? Okay, can y'all imagine what that might feel like? So you pull that parachute, it opens up, it catches, it has that air resistance, it slows you down, and then you kind of feel like you're just floating as you get closer to the earth. You're not accelerating downward per se, like you're not like a dart towards the ground. You're just kind of easily making your way down. You're floating down. That is terminal velocity. Once that parachute pulls and it catches all the air resistance it can, it matches that gravitational force of you falling, slows you down, and then you reach your terminal velocity where you're no longer accelerating. You're just kind of floating is the best way to picture terminal velocity. Okay? All right. We have three more forces. We have a tension force, okay? Tension, I want you to think of a rope, all right? Or a pulley or a cable or something like that, okay? So anything that involves a type of wire, a string, a rope is going to be our tension force. Spring force is exactly what it sounds like when there's a spring involved. That can be a spring collapsing or a spring expanding, okay? And then buoyant force is also pretty self-explanatory. Anytime that something is floating on water, that water is providing a buoyant force. Okay? Those three, they kind of speak for themselves, so there's not a whole bunch of explanation going on there. Okay, so I need you to, on this first page, is just all about those different types of forces. I need you to get familiar with these. Okay, that's actually going to be what our exit ticket's about later. But the sooner that you can kind of memorize what each force does or what it involves, the easier this unit will get for you. Okay, now that we have types of forces, we're actually going to start today by looking at what those forces do with each other, what cancels out what, and how to interpret that. Okay, we're going to start looking at these things called free body diagrams. That's a physics term. They are a lot simpler than they sound. Okay, whenever I took physics in college, my professor drew this weird thing on the board, and he's like, "This is a free body diagram," and I was like, "This is going to be a long semester." But it's actually a lot easier than you think it is. Okay, so let's go ahead and take a look at that. Forces on an object can either be balanced or unbalanced. Okay, balanced, all the forces are going to cancel each other out. The object will continue to do exactly what it has already been doing. Okay, so that is balanced. Everything cancels each other out, all that fun stuff. Unbalanced, the forces do not cancel each other out. So this is going to cause a change in direction or a change in speed or something like that. Okay, unbalanced causes a shift in things. What I want you to pay attention to on balanced forces, and we'll see more of this in our examples in just a second, is that balanced can mean either at rest or constant speed. Okay, balance can be both ways. Unbalanced, there's going to be a change in something, a change in speed, so we have some sort of acceleration, or a change in direction. Okay? And we'll see what that looks like more in just a second. All right, here we go. So these are free body diagrams to the right. Okay, we're going to write down a little bit of information about them. All that a free body diagram is, it's a summary of what's going on. Okay, it's a summary of what forces are happening on a certain situation. Okay, I like to use boxes. Okay, so whenever I draw free body diagrams, I draw something like this. If you like to use the point system, you can do that as well. Okay, I like boxes. It's kind of easier for me to see that way. And then talking about the new unit, we've learned force is measured in newtons. 1 newton is equal to 1 kilogram by meters per second squared. Force is going to have direction and magnitude. Okay, so if there's a force moving to the left, we got to denote that. Okay, so force has direction and magnitude. Okay, so what we're going to do next in our notes is look at different examples and start interpreting these free body diagrams. Okay, getting used to looking at them and understanding what they're telling us. All right, so example 1, a physical science book is at rest on a table with a balanced force. Fill in that blank for me. Balanced force. Okay, so I can tell that it's balanced because these arrows are the same length. Okay, most of the time there's some free body diagrams where this would be maybe like a really short arrow, then it wouldn't be balanced then. Okay, but since the arrows are the same length, this is a balanced free body diagram. Okay, does anybody remember what force is Fn? The opposite of weird. Normal. Okay. So this is the normal force pushing up. So that would be like the table pushing up on the book. And this is Fg, gravitational force, where that book wants to fall, but that table is pushing back up with normal force. So it's balanced. Okay? That is a balanced free body diagram. All right. On this one, a student shoves a physics book and lets go. This is unbalanced. Do y'all see how these arrows are not the same length? That's how we know that it's unbalanced. Before we ever put any numbers to it or anything, the friction force is not the same as the applied force. Okay? So that would be an unbalanced free body diagram. Alright, and then we still have normal force of the table, gravitational force, that book wants to fall. FA is applied force. So the applied force here is that person shoving the book. Okay? The friction force is that book rubbing against the table, causing friction. Okay? So those are the types of forces there. This is unbalanced because friction force is smaller than applied force. Okay? That is unbalanced. Example 3. It doesn't give us a situation this time. We got to decide for ourselves. Is this balanced or unbalanced?
Unbalanced.
Why is it unbalanced?
Because the gravitational pull.
Right. Okay? It's unbalanced because this arrow is bigger than this arrow. Okay? So, direction of acceleration. Which direction do you think this is going?
Down.
Down because it has the bigger arrow. Okay? So the direction is down. And what is the object doing? Moving and accelerating downward. Okay? And that's because there's a bigger pull down, and we see that because of the bigger arrow. Okay, so free body diagrams, are we okay with those? They're not too bad, right? You just got to read what's going on with the arrows. All right, next example. Would you say that this is balanced or unbalanced? Balanced because
It's even.
the arrows are the same size. Okay, so that is a balanced free body diagram. Direction of acceleration, we're going to say none. And then what is the object doing? This is kind of a big kicker of the note, so I want you to really hear me when I say that balanced forces can be at rest or constant motion. Okay? It didn't give us a backstory, so we don't know if this is something resting on a table. We don't know if this is something going at a constant motion. We just got to remember that if it's balanced, it can either be at rest or in constant motion. Okay, balance works both ways. Okay, we have one more little part that we're going to get through in our notes, and it's just an expansion on these free body diagrams. So, we've looked at them and they don't have any numbers on them. We're now going to look at them with numbers, okay, with newtons of force and things like that. We're going to calculate net force. All right, go ahead. There's a definition section at the very top of this page. I want you to write the definition of net force. The sum of the forces taking into account direction. The sum of the forces taking into account direction. So now, we saw the same free body diagram, okay? If you look at just the arrows, would you say that this is balanced or unbalanced? It's unbalanced, okay? So now, they have numbers to them. We can see that our applied force is 100 newtons. Our friction force is only 10 newtons, okay? Our gravitational force is equal to our normal force, all right? So if we were to calculate net force, we look at direction and numbers. So, Fn and Fg cancel out. Do y'all see why? Because they're both 500. All right? Fa is 90 newtons more than Ff. So our net force is 90. And if you need to write all of this out just to have an understanding, please do.
You're just subtracting everything?
Pretty much, yes. So if they go opposite of each other, you want to subtract to get net force. Okay, so if I did 500 minus 500, it's 0. So they just cancel out. 100 minus 10 is 90. So our net force is 90.
What if that wasn't 500? Would you still if it was like 400? Would you still
Yep.
subtract that total by 90?
So we would have, like if this was 400, we would have 190 net force.
Oh, yeah.
We would have this net force and this net force, so it would be 190 net force. Okay, most of the time that's not the case because objects only move in one direction.
Mhm.
Okay, so which direction would this be going? These two cancel out, so there's a greater force going that way, so it's going to be moving to the right. Okay, so we can get a whole bunch of information off of these free body diagrams. Okay, they tell us a lot of stuff. All right, let's look at this next example. Balanced or unbalanced? Unbalanced, because there's nothing opposing this one over here. So this is still an unbalanced free body diagram. What would you say is the net force? 100. 500 minus 500, they cancel out. All you're left is with 100 of applied force because nothing cancels it out. So our net force is 100 newtons. Which direction is this moving?
Left.
To the left. Okay, so net force isn't all that bad, right? This is easy math compared to what we've been doing in Unit 7. All right, so this next one, balanced or unbalanced?
Balanced.
Balanced. What would the net force be?
0.
0. Okay, so Fn and Fg cancel each other out. So our net force is going to be 0. Okay, this one, direction of acceleration. Let's talk about this. So our definition of a balanced force says that it's going to keep doing what it's been doing. If I read, it says a zombie hamster rolls along at a constant speed to the left. So if this is balanced, it's going to keep going at a constant speed. I need to add to the left here. So constant speed to the left. I need to add that on here. Balanced forces or balanced free body diagrams keep doing what they've been doing. This tells us that it was moving constant speed to the left. So that's what it's going to keep doing, is moving at a constant speed to the left. All right. Next example, maybe if my mouse is going to work. There we go. We have a zombie standing still. Is this balanced or unbalanced? Balanced. Net force? 0. And then what would the direction be? At rest. Good job. Okay? So balanced forces will continue to do what they've been doing. This zombie is standing still, so the direction is going to be at rest. Okay? It doesn't change because it's balanced. All right, last example of our notes today. Ask us a question. Is this zombie moving or at rest? How can you tell? So first of all, do we have a balanced or unbalanced free body diagram? It's balanced, okay? And so we're going to be smart and we're going to say the forces are balanced, but you cannot tell if it is moving at a constant speed or at rest. Okay, we don't have any information to if it's moving or not moving. We just know that it's balanced. You think I can handle net forces? It wasn't too bad, right? Okay, you're getting a new vocabulary sheet. This time I made them green. Last unit they were blue. If you keep up with this and you have it completely filled in, you get extra points on your test. So like for unit 7, if you had a completely full blue paper, you got extra points on your test. That's how Carly made a 111 on her test. Okay? So what we're going to do next is we're going to write in vocabulary words from this notes that we have done, and then you do your exit ticket about types of forces. Sound good?